Welcome back to this series of talks on population-specific bundle atlas creation. In this second and last talk, I will dive into the actual methods we can use to create wet matter bundle atlases. I will start by providing an overview of the bundle atlas creation problem. Then I will summarize some of the existing methods in the literature, and I will finally explain and describe in detail our new tool for bundle atlas creation, which is called BundleAtlasing. This will include an overview, details on registration, bundle combination, and some interesting results we have obtained so far with PPMI data. So let's define the problem we are trying to solve. When we are trying to create a bundle atlas, we have an input, which are the subject diffusion weighted images, and we have a clear output, which are the bundle atlases based on streamlines. We have a constraint, that is that we want to represent the average anatomy with those atlases. But apart from that, that's conceptually the idea. The problem here, of course, or the key challenge is how are we going to fill in the block in the middle? How are we going to create an atlasing method? So that is indeed quite challenging, and there has been some research work on this matter. The first approach I want to mention here is an atlas that was created a few years ago. It's called HCP 842 because it was created based on human connectome project data. And the approach the researchers followed is quite interesting. They started from raw diffusion weighted images, and they performed registration and diffusion model fitting for each subject independently, and then they created a template of fiber orientation distribution. So after fitting the diffusion model, they averaged the ODF values to obtain a template of fiber orientation distribution. And from that template, they ran tractography only once. So the tractogram they obtain is, let's say, cleaner than the average tractogram. And finally, they extracted the bundles from that clean tractogram to obtain those nice looking bundle atlases shown in the right. The atlas is might be very useful and is available either from the original source or also from Dipy. Another interesting approach was developed almost at the same time, and in this case the approach is quite different. They performed the model fitting and tractography separately for each subject, and once they had created the tractograms for each subject, they performed first a group-wise registration to align all the tractograms, and then the atlas was created based on clustering. So instead of segmenting the bundles specifically, they developed a clustering algorithm that clusters the streamlines across subjects, trying to preserve or cluster together those structures that are more present in the population. So that algorithm goes from having a full tractogram or a set of tractograms overlapping to a specific, let's say, bundles or similar structures that are consistent across many subjects. As with the previous approach, the atlas is available online and might be accessible from the original source. So now that we have discussed a couple of approaches, let's say that we are in a different situation. We have watched all the videos from the workshop and we have been able to perform tractography and bundle segmentation, and in the end we have a bunch of segmented bundles from several subjects already available. And let's say that our goal could be to compute an atlas from those already segmented bundles and try to obtain a streamline atlas that represents the average anatomy on all those bundles. In this scenario, the previous methods don't work quite well, because not because they are wrong or whatever, but because they are not designed for that. So the first approach works at ODF level, so it doesn't work with streamlines directly. And the second approach was developed to work with tractograms. So don't really answer the question we are trying to address here. And that's why we started to think about this problem, and we started to think, how can we create an atlas from already segmented bundles? How can we combine those bundles? And once we started thinking about it, two main questions arose immediately. The first one is, how are we going to align those bundles to the same space? So how are we going to go from the left image to the image in the middle? And even if we get there, how are we going to merge or combine those bundles into a single one that somehow captures the underlying anatomy of the population? So thinking about the problem, we came out with BundleAtlasing, which is our new tool for population-specific bundle atlas creation. The whole process is performed in the space of streamlines. That basically means that we are working with streamline bundles from the very beginning. So we assume that you already have your segmented streamline bundles, and after that we start the processing. And the strategy we propose here can be summarized with the image in the right part, and it's a pairwise tree combination strategy. It's easier than it looks like, probably. So the idea is that at the top level we have our input bundles in native space, not aligned, not registered to each other. And what we do here is iteratively we make pairs, we randomly match those bundles in pairs, and for each pair of bundle we register that bundle. I mean, we register those two bundles and we combine them into a single one. So instead of trying to tackle the big problem of aligning and combining multiple bundles at the same time, we perform the whole procedure pairwise. And the idea is that at each iteration we obtain half the number of bundles we had in the previous level. So after a certain number of levels, we just get one bundle, and that bundle is what we consider to be the atlas of that population. Here, of course, the key question is how are we gonna register and combine each pair of bundles, and that's what I will explain right now. So the first thing we want to do here is to register each pair of bundles so that they are aligned. Here we could follow the regular approach of registration, in which we define one bundle to be the static or reference bundle. This is going to be our target space for registration, and the other bundle is going to be the moving bundle. That means that we are going to try to find transformation that moves the moving bundle so that it overlaps with the static bundle. This is already available in Dipy and it's called the streamline linear registration. So briefly, streamline linear registration is based on pairwise streamline distances, and how it works is that we have both bundles in native space or not aligned, and we compute the distance between each streamline in the static bundle to each streamline in the moving bundle. So we create this distance matrix, and after that we summarize all the information in that matrix in what is called BMD, or bundle minimum distance, that basically takes into account all the minimum distance for each streamline in each row and column. And the whole registration process aims to minimize that distance by changing up to 12 parameters in case we are working with an affine transformation. So we are trying to obtain those 12 parameters that minimize that distance, BMD distance, between the moving and static bundle. So far so good. This is the regular approach used for registration, but has a problem when trying to build an atlas. It's that this approach is designed to move one bundle to the other. So we are assuming that the static bundle is a good reference for registration, and of course the results will be highly biased by the bundle we chose as static, since that's indeed the whole purpose of the method. But if you think carefully about that, when we are trying to create a new atlas and we are applying our pairwise tree registration and combination strategy, we have no clear static bundle. We want all bundles to contribute equally to the procedure. So it's a bit an issue for us to have a result that is so biased by the bundle that is chosen to be the static. So to overcome that problem, we developed an extension of the regular streamline linear registration, or SLR, that we call halfway registration, or halfway SLR. In this scenario, instead of defining a moving and a static bundle, we allow both bundles to move. So we have moving one and moving two bundles, and the idea is to find two transformations that move both bundles to a space that is in the middle, or halfway the full transformation. So it's in the middle, in between both bundles. So the idea is that we align both bundles, but not to at the space of any specific bundle, but to a space that is defined in the middle between both. This way we are avoiding any kind of biases, as the result is just defined by, is defined by both bundles, so both bundles are contributing equally to the space resulting from the registration. So a problem with this approach is that if we allow both bundles to move, potentially we could move both bundles to any point in the space and achieve a good overlap. So we are facing a problem with infinite solutions, and of course that's not good for optimization. And what we did here was to constrain the search space. So we provided a clear and accurate definition of what a halfway space is, and in this case we defined the halfway space as the space we obtain by taking half the value of the full transformation. That means that, for example, if the full transformation between one bundle to the other in the translation in the x-axis, for instance, is 3 millimeters, we take 1.5 from one bundle and 1.5 from the other bundle in the opposite direction. So we are moving one bundle in one direction and the other one in the other direction. And the trick here is that for each transformation value, translation, rotation, scaling, and shearing, we applied opposite values for bundle 1 and bundle 2 with the same value but in opposite directions, so that they both move to the space that is in between. This way we are optimizing 12 parameters as we did before. An interesting application of this halfway registration is that since we are able to align both bundles to a space that is not biased by any of the two bundles, we can extend this idea or this logic to a group-wise registration setup, in which, for example, let's say that we have 4 forceps major bundles, and we would like to register them group-wise, without having any atlas or any kind of reference. So what we can do is iteratively we make pairs and we move each pair to a halfway space. So we have first 4 bundles in native space, and then in the first iteration we register the green with the light blue bundle and the pink with the red one. So each pair gets aligned, and the overall group distance, the mean distance between all the bundles, decreases. And after several iterations, that group distance basically converges because all the bundles are already overlapping and we cannot increase the overlapping more. So we achieve a group-wise registration that is unbiased in a really natural way. If anyone is interested, there's a current open PR in Dipy implementing this kind of approach. As I mentioned before, the pairwise tree strategy of BundleAtlasing has 2 main key elements. The first one is registration, what we just discussed, and the second one is bundle combination. So now we have already solved the registration problem, so we have each pair of bundles is already aligned, and the next question is how do we combine them into a single one that captures the anatomy or the traits present in both bundles. So to do this, we propose a streamline matching and averaging approach that consists in 3 simple steps. The first one is streamline matching, the next one averaging, and the last one selection. So let's go step by step. In the first one, we have both bundles already overlapping, and what we do here is we apply a streamline matching procedure that aims to find unique correspondences between streamlines in both bundles. So we are trying to find matches, or let's say find pairs of streamlines that are very similar between both bundles so that we can average them, right? So let's say, for example, here we have a toy example in which we have a matrix of 4 by 4 representing a super simple case in which we had only 4 streamlines per bundle. So we have S1, S2, S3, and S4 for bundle 1 and for bundle 2, and we want to assign correspondences from each streamline in bundle 1 to each streamline in bundle 2. And to do that, to solve this kind of problem, there are several strategies, and in fact this problem has been solved in many other fields before, and it's called the rectangular linear assignment problem, and was recently introduced to the field of diffusion by Olivetti et al. In a recent publication. And the idea is that we optimize the sum of distances. So we frame a problem in which we are trying to find matches so that we minimize the sum of distances. So we need to consider that we need to find unique matches between streamlines in bundle 1 and bundle 2 so that we minimize the overall distance, not each individual pairwise distance independently. So for example, in this case, that would be the matching. Those white and red dots mark the correspondences found by the algorithm that, by the way, is available in SciPy, and it's very fast, at least in our experience. So here it's interesting to see how the fourth streamline of bundle 1 was not matched with its closest streamline, that would have been the third, but it was matched with the second. And that's because we are not allowing to match a streamline more than once, so we want unique matches. The second step of the procedure is what we call a streamline robust averaging. And now we use the matches found by the previous step to perform averaging and aggregate information. So for each pair of streamlines that were matched, we get the distance. So here in the example, let's say that we have two streamlines. Obviously, this is an example. Usually, if those streamlines were matched together, they would be much closer, but it's just an example. So let's say that we have those two streamlines. We compute the distance, and we set a threshold, and we say if that distance is below a threshold, we consider that pair of streamlines to be equivalent, and we average them into a single one, in this case the red one. Otherwise, we don't perform any kind of averaging, and we go ahead and keep both. Okay, so what we do here is that depending on the threshold we set here, the distance threshold, we are changing the level of smoothing and averaging of streamlines pairwise. So we repeat all this procedure for all the streamlines that were matched, and we go ahead. The last step is the streamline selection. So that means that we started with a number of streamlines in bundle 1 and another number of streamlines in bundle 2. We performed the matching, the unique matching, and if the number of streamlines in both bundles is not the same, some of the streamlines were not matched, so they went directly to the third step. And also in the second step of averaging, depending on the threshold we selected for the exclusion criteria, some of the streamline pairs that were not close enough were not averaged and were also excluded temporarily for the third step. So in this third step, we perform a random streamline selection and we aggregate together those streamlines that were averaged in the second step with those that were not averaged or that were not matched. This is important because in certain cases, when we are working with really heterogeneous data sets, it might happen that some bundle has that a bundle has many less streamlines than the other one. So after the matching, we have very few matches, and if we just keep those streamlines that were matched, we would iteratively decrease the number of streamlines in our bundles, and we want to keep the number of streamlines consistent across the whole pairwise matching tree. And with that, we would finish the bundle combination part. So remember that we are working with a tree in which we we create pairs of bundles. For each pair of bundles, we apply registration, unbiased registration, and then we apply bundle combination. So this is again the figure that describes the whole procedure from the input bundles to the last bundle, which is the atlas. So we have started testing our new method. We are currently working with a dataset derived from Parkinson's Progression Markers Initiative data, PPMI. It has segmented bundles from 32 subjects, and the dataset is available online in case anyone finds it useful. And it's a good example of how to use Dipy for processing, as all the steps required to generate the dataset were carried out in Dipy. Here we have some of the results with the left arcuate fasciculus. In the left we have 9 out of the 32 bundles, input bundles from healthy subjects, and in the right, the atlas that was generated by using BundleAtlasing. You see two opposite examples. The first one is without any kind of averaging, so putting a threshold that is so low that we never consider a couple of streamlines to be close enough to be averaged. I'm talking about the second step of the bundle combination part of the methodology, while the second one is applying a really strong averaging. In that case, we set a high distance threshold so that we consider that many matched streamlines are close enough to be averaged. So we obtain very clean results. Similarly, with the corticospinal tract, here we have the 32 input bundles and the atlases we created. We see that the atlas with no averaging is rather noisy, but if you look carefully, the input data is itself noisy. So if we are not averaging anything and we are just aligning the bundles and let's say selecting streamlines randomly, it's expected that we will obtain noisy results because the input data looks like that. What we can do here is, of course, apply more strong averaging to obtain cleaner results. So finally, yes, I think it's interesting that our methodology provides an easy way of obtaining atlases from the certain population with a different kind of smoothness. So by just changing the distance threshold in that bundle combination step, we can obtain atlases that are very noisy or that capture most of the variation in the data, or we can obtain much smoother atlases that only really capture the information that is very, very present in most of the subjects under study. So just to mention that this is still work in progress and we plan to validate it with a larger data set. We also are working on how to incorporate non-rigid registration into the pipeline, and in case anyone has interest, you can check a PR that is currently open in Dipy. So finally, as take-home messages from this talk, I just want to give you 3 ideas. The first one is that creating population-specific bundle atlases can be quite challenging, but nonetheless, there are very useful approaches in the literature that cover very specific and interesting cases, and that we are proposing a new method called BundleAtlasing that is, say, new and that operates at the level of the streamlines, is based on pairwise and bias registration and bundle combination, as I mentioned before, and is able to create population atlases from segmented bundles with different kind of smoothness. So thank you very much for your time. I hope it was interesting. In case anyone has any kind of question, idea, criticism, we are open to discuss the project, as it's currently still something we are working on, and we will be more than happy to discuss with you any kind of the details. I hope you enjoyed the next part of the workshop.